Welcome Year 12s to this video. In it, I'm going to run through Module 2, which is our Networks module for the Exam 2 trial that you have completed. I'm going to run through in more detail the more challenging questions. I have already written solutions for some of these questions, and I'll obviously just go run through them a little quicker. So our question here is based around a zoo. We've got a network that represents the paths between these different places in the zoo, so different exhibits. We've also got an entrance and we've got a cafe as well. So our first question looks at the shortest distance between the entrance and the seal exhibit. So you first want to identify those two places on your network, and then you want to consider the lengths between the paths and the different routes that you can get from the entrance to the seal. So it is a fairly easy question because if you have a look, we can simply go from entrance to P then to S, and we can see that that's a length of 45. And it's very quick to see as well that going any other possible route to get to the seal exhibit is definitely going to go over the 45 meters. So we can get that answer very quickly. We've got Freddie visiting the zoo and he wants to visit the cafe and each of the animal exhibits, just once though, and wants to start and end at the entrance. So in other words, looking at the network here, he wants to get through all of these vertices, he wants to visit every vertex, and he wants to come back to this starting point. Of course, when we're looking at visiting every vertex, that's Hamiltonian or Hamilton, and since he's starting and finishing at the same place, we call that a cycle. So Hamiltonian cycle is the answer to that one. There's a few different answers for the route, but basically you just want to see drawn on your network that every vertex is visited, but only once will you visit each vertex. So like I said, there are a couple of ways that you can do this, which is why it says one possible route, and you'll see in the solutions that you have access to some of the different options for that. Over the page, a little bit more challenging now, we're going to add an exhibit, and we're told some information about the paths to that exhibit and we need to add them on. So first of all, the reptile exhibit is R, so we need to make sure we have a vertex on there that is listed as R, but what you want to do is have a look at where it's going to go. It says new path of 20 meters is going to go between the reptile exhibit and the giraffe exhibit. So you want to make sure you place R so that you can attach it to G. But then reading ahead, we see also that the reptile exhibit is going to connect to the cafe. So I've just placed it right in between G and the cafe. And then I've put the lengths on, so 20 and 35. Make sure that you do put the lengths on because that was required. You'll see here, write the distances on the edges. You needed to have them there too. Okay, so the new paths are going to reduce the minimum distance that people need. People are going to walk between the giraffe exhibit just here and the cafe. And we want to know how much distance is saved. So by how much will these paths reduce that distance between the giraffes exhibit and the cafe? So really we need to look at two things. Now we can get from the giraffe exhibit to the cafe in 55 meters, so 20 plus 35 in other words. What we want to know is what it was. Now you'll notice that I've put it was 140 meters. So how did I get that? Well, I had a look at how I could get from here to here without going through those new paths. So you could go this way, and I think you get 145. You can go down this way though, so to L, T, M and the cafe, and you get 140. Likewise, if you go through this way up here, you also get 140. Going through that way over there is a bit longer. Likewise, just before I said I had 145 through here. So the minimum distance before was 140. And so from here, all I have to do, so therefore, 140 minus the 55, so what it was and what it is now, and you'll see that I've saved 85 meters. So it will reduce the minimum distance by 85 meters. Over the page now, you'll notice for this question, a forward and backward scan might be useful. It's not absolutely necessary. Those of you who are very good with your critical path analysis might be able to do this without the forward backward scan, but I know for the vast majority of you, you will be doing the boxes and putting those numbers in. And that is to answer part B and C. So first of all, part A, which activities have more than one immediate predecessor, what I want to see is this sort of situation. I want to see which activities have got two or more things before them. So if you have a look here, D has got C and B as a predecessor. G as well has got E and F. And if we look at I, it has G and it has H. So only those three activities have more than one thing preceding it, so before it. So you're looking at more than one edge coming into its starting point. Now the critical path is obvious once you do your forward backward scan. As you can see, I've done mine. So it goes up through here, A and then C, then across to D and up through F, G and then I. So in other words, you're looking for the longest path. And that's what I meant before by some people don't need to do a forward backward scan, because some people would be able to just very quickly find the longest path, and then you've saved yourself having to do a forward backward scan. The thing is though, part C has asked for that latest start time for activity B, and this is where a backward scan is really helpful, because really it's asking for that bit right there, the LST. Doing the forward backward scan for something like this is fairly quick because it's not too complicated a network. So I would recommend doing it for the vast majority of you, because it is going to be, I think, a more accurate way to arrive at your answer. One way that I do it as well, one thing I consider is the latest start time from B. Really, you can just look at the different paths that get to this point, that get to D. You'll notice that there's a path this way going through A and C, and that's got a length of 7, so the 3 plus the 4, whereas B has got 5. So see how the difference between those two paths is 2? That's a bit of a clue. Well, that's where this 2 comes from. It means that going this way is 2 less than going that way. So that's our second last question. Most of the time, I think we're going to be spending on this last one, which was a very time-consuming question, number 3. First of all, we had the Hungarian algorithm being used. One thing to keep in mind, though, when you read this question is that the cost is in 100,000s. So this value, for example, is not 13, it's 1.3 million. So 13 times 100,000, in other words. Or if I grab another one to show you this value over here, which is 4, just here, it's not actually $4, it's $400,000. So it is important that for the last question in particular, that we've recognized that. Okay, so lots of reading here because they go through the Hungarian algorithm. They basically spell it out in this question how to do it. They've done there's our original matrix or original table. Then they've done the row reduction. And then, of course, in this third question here, and I've already written on it, they're actually asking us to do the column reduction. So since we've got the row reduction already completed here, what we'd be doing is looking for, see how these ones are already done and this one is done for us in the next table. We're looking for the lowest number in this column, which is 5, and then we're going to subtract 5 from each of these numbers. So we'd get 0, we'd get 1, 1 and 2. So they're the numbers that are required for the answer to our next question, the 2, 1, 1 and the 0. And you'll notice I put them in there. So that is simply from doing a column reduction. The next one is asking us to do the next step in the Hungarian algorithm, which is to add the lines onto the zeros, so to try and cover the zeros. So what I can see is I've got 2 of them here in this row. I've got 1 here and 1 here, so I've got another 2 in that row, and then I've got 2 in this row here. So really, what I'm going to be doing is covering, and I am told that it's 3 lines that I need to use, and I'm simply placing them on like so. Now, the next question does state an allocation is not yet possible. So it does mean we're going to have to go and do that next step. And that is the final step, looking at the uncovered numbers. And only then will we be able to answer this question. And that is the final allocation. So what we're going to do, I'm going to do it just on the side here. Just so that it's not written over the top of that. That's already getting a little bit busy, so I'm going to do it to the right of that. So looking at my uncovered numbers, I've got 2, 4, 6 of them, and the lowest one is right here, which is 1. Now, what's going to happen is I'm going to subtract 1 from all of the uncovered numbers, so that would leave me with 1 and then 0, 4 and 4. Now, these 2 zeros here, they're going to stay the same. So they've got just the 1 line through them. I'm going to get 1 and 2 here. Anything that's just covered by 1 line is going to stay the same. So I'm just writing them out. And then finally over here, that minimum uncovered that I subtracted, I'm going to add to these 2 here, making it 3 and 2. Okay, so from here, I want to be able to allocate. I wanted to quickly check, though, that I've got 4 lines. So I've got 2 zeros here, so I could put a line through there. I'm sort of just doing it in my head just so I don't mess things up. I can go through there. I'd still need 1 through here. And then you can notice I've still got 3 zeros here that I can't cover with 1 extra line. So I am going to use 4 lines to cover this. So what that means is that I am ready to allocate. Now, to allocate, you can draw a bipartite graph. So you could do that on the side here if you want. I don't always do that. I allocate slightly differently, which I'll do in a second. But just for those of you who do it with this method, we look at our zeros. Whoops, I've gone too far. We look at our zeros. So for business 1, there's only 1 0, so they're going to do task 3. Business 1 is going to do 3. They have to because there's no other option for them. You can see business 2 can do 1 or 3. So generally you would do this. You'd go business 2 can do 1 or 3. But since we've just allocated business 1 to task 3, business 2 has to do 1. Like so. Business 3 can do the second one or the 4th one. And business 4 can do the first one or the last one. So the first one or the last one there. So if we have a look at then who can do task 2, only business 3. Like so, which gives us business 4 doing task 4. So there's our answer to part C with allocated. Now I mentioned you don't need to do a bipartite graph because this method as well is useful. I can see that business 1 has to do this task because it's the only 0 in that row, which means I'll then cross this out because they can't do that task. That leaves me with only 1 0 in this row, which means that business 2 can't do those ones down there or that one. And they also can't do these ones. So we just put a cross through them and we can see that business 2 is doing task 1. Then I can see another 0 on its own in this row. There we go. So that means they're not doing that one or any of these, and that leaves me with this 0 over here. And then of course we can allocate from those zeros that I've put in boxes. That saves some time sometimes rather than having to do this and then convert it just to your final allocation. So remember, we don't want, because we want the allocation only in here, we actually don't want all these extra edges, only the ones showing what we have allocated. Finally, we are going to get to this final question, which is the very time-consuming one. As we can see, it's saying business 4's changed a quote. So we're actually going to change a number in our very first table. We're going to then allocate. So we're going to do the Hungarian algorithm again. We're going to get the new cost or total cost after allocating again. But the main thing is we want to see what the reduction is in that cost. So we actually need to know what the total cost is for this allocation. And that's what I'm going to do to start off with. So if we have a look at what we've allocated, I'll just go back to this one just so that we can add the numbers up. We allocated business 1 to task 3. So this one, business 2 was task 1, business 3 was task 2, and business 4 was task 4. So if we add these numbers up, we've got 10 and 5, so we've got 15, plus 8, so we've got 23, plus another 8. So we've got 31. So it's not actually 31, it's 31 times 100,000, but I'm not going to multiply it out, I'm just going to keep this number because that's actually all I need after I do the same with this one over here. Okay, so we want to allocate again. So I'm going to go back now to this original one. And I'm going to change the quote. So the business 4 has changed their quote for the construction of the pathways. So it's this number here that needs to change. This number here is going to change. They've said it's now, the new cost is $1 million. So $1 million, we want to know what that number is. So you're basically doing 1 million divided by 100,000, since this is in 100,000s, and that gives you 10. So we need to change that to 10, and then we need to do the Hungarian algorithm again. Now, in terms of space, I'm going to use this space down here just to write it out because I don't like doing it all on one table. So my new values are, I'll just read it off my page, 12, 10, 12, 10. And then these ones are staying the same. Now, if you're pretty confident with your Hungarian algorithm, you can skip ahead rather than watch me do this. From here, we're going to do our row reduction to start off with. So our lowest here is 5, so I'm going to subtract 5 from each of those. I'll just put a line so I can see the division. Subtract 5 from each of those. Lowest here is 4, so we're going to subtract 4 from each. Lowest here is 6, so we'll subtract 6 from each. And lowest here we've got is 8, so we'll subtract the 8. Now, hopefully that hasn't chopped off. Might chop it off a little bit in my my recording screen. Okay, so I've got 7702, 6703, 6220, and 2310, just in case you can't quite see what I've written there. Now I'm going to go to column reduction. Now the good thing is there's 2 columns here that already have zeros, so I'm going to write them out first. These first 2 columns though, they don't. So the lowest in the first column is 2. So 7 minus 2, 6 minus 2, and 2 minus 2. The next one, the lowest is 2 as well. So 7 minus 2, 7 minus 2, 2 minus 2, 3 minus 2. Okay, so now from here, I'm going to put my lines on. I might just use these red ones. I've got 2 here. I've got 2 there. I've got 2 and 2. So I can actually do this just because I need to use the minimum possible. There we go. So I can do it in 3, which means I do my final step now. Lowest is 2, so I'm going to subtract 2 from all of those uncovered numbers. There we go. I'm going to add it to these 2, so that becomes 4 and that becomes 3, and these ones here are going to stay the same. All right, so now I've got 2 zeros there. I've got these ones. I'm going to have to use 4 lines here. So there, 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 and there, in other words. I can allocate now. So look for any zeros on their own in a row or a column. I can see this one. Any other zeros? Oh, by the way, because I've done that, I'm then going to circle my original one too. There we go. Any other zeros on their own? Well, that's not going to happen now, so we cross them out. So this one will have to happen, which means none of them do. And next we've got this one that has to happen, and then obviously this one. So I've got all these numbers in this diagonal. That's my new allocation. So what I'll do is now I'll add that up to see what total do I get. 10 and 8 is 18, 18 and 4 is 22, 22 and 7 is 29. So just over here to this page, how much is the reduction? So it was going to cost 31 by 100,000 and now it's going to cost 29 by 100,000. So altogether we're going to save 2 lots of 100,000, which is a $200,000 saving. Okay, so as you can see, it was fairly time consuming. So it is really important that you're able to do your Hungarian algorithm fairly efficiently, because what you'll notice then is that I didn't need to keep looking at notes. I didn't keep having to read through the steps. If I've practiced that algorithm enough, I should be able to do it very quickly. And that's where students are advantaged here. If you can do your algorithms with some efficiency, you've got enough time then to finish this exam. So I'll leave it there. If you've got any additional questions, you do need to come and see me in class or arrange to see me outside of class.